Yes, sir.
Yeah. So let us, because this way we know what to solve systematically. So let us look at this. So this will continue with problem. Let me see where to. Yeah, we did that one. Yes, let's do problem 1.14. Okay, so this will
Yes, sir.
be
I'm just getting the PDF.
right. I'll write the question here. So problems from Artin algebra book. So I'm writing the name of the author first. Right. And we are doing this problem number 1.14. Yeah. So 1.14,
Okay.
and
Yes.
this is chapter 1. So let's write that also. Okay. Yes, so Virendra, you are here. So we are solving problems. So I'll just write the problem on the board and then we'll just try to solve it. Okay, this will be all from Artin's book. So yeah, question is find infinitely many matrices. Find infinitely so such that BA is I2. Okay, so I2 is identity matrix of size 2 when A is equal to this is 2 1 1 3 2 1. A is right. So what will the dimension of B be?
Uh,
Yeah,
2 by 3, sir.
2 by 3, right? So yeah, let us just try this.
So I guess we just take some arbitrary like A, B, C, D. Or
Okay, yeah. So let's just think for a minute and see if there is some
yes.
some elegant way and okay. So yes, so let us see. Aryan,
Yes, sir.
so
So
what is your method?
my idea is to take B as A, B, C, D, E, F, like general 2 by 3.
Okay, general 2 by 3. Okay, I'll just write it in this way.
Yes. B, yes, sir.
Yeah.
So now, what actually happens is when we perform the multiplication, we get BA is equal to
Mm-hmm.
so using your notation, so it'll be 2B11
Mm-hmm.
plus 2B12 plus 2B13. Oh no, sorry, plus B13. That's all. Just B13.
Okay.
And then the next one is is 3B11
So you mean in the first row?
Yes, sir. Yes, sir. That one. 3b11 plus 2b12.
Right.
Oh, okay. And then in the first element, sir, it's actually b12, not 2b12.
Right, this one, right? Yeah. Yeah. So
Yes, sir. Yes.
Virendra, you
Yeah. Now
should
it's
just
correct. Yeah.
also just check it if this calculation is correct. And yeah. Okay.
No, there's one more term, sir. It's plus b13. Yeah, in the last.
Hmm. Right, of course. Right. Plus B13 or B23?
No, no, sir. b13 only.
Okay. No, that doesn't, that's not. Oh, yeah,
Uh,
sorry, that's correct. Yeah, sorry.
yes, sir.
Yeah, right. And then we
Uh,
do the same thing, but this one replaced by two.
yes, sir. So it'll be 2d or 2b21. Yeah, plus b22 plus, yeah.
Right. This is okay, but you see, like, let us see how we can solve this, and then.
Yes, sir. So like what actually happens is if we equate this to
Hmm.
I2, we get
Right.
four equations and they're actually like consistent, and you can treat two of these variables as parameters and solve the rest. So you'll have four equations and four variables if you treat two of these variables as parameters. So and then you
Hmm.
can change the parameters as you want, so you get infinite limit.
No, but you don't have two equations. You have four equations.
Yes, so four equations and six variables. So treat two of those variables as parameters. Say you treat b11 and b21 as parameters. We
Right.
solve the rest in terms of these two, and then we'll actually get like infinitely many solutions.
No, that how do you know you will get infinitely many solutions?
So like you can just solve this. So what I did
Yeah.
was when you compare, you'll get two b11 plus b12 plus b13 is one. Like if you just equate these matrix elements,
Mm-hmm.
we'll get four equations. So this will be equal to one.
Right.
Then next one 0.
Okay. And actually, this so the second system is completely independent of the first system.
Yes, yes, yeah. It's only the yeah. So it should be one. Yeah. So now like solving this.
Okay. Let me think. Like conceptually, how do you say that there are infinitely many solutions? Saying that you can solve this in terms of the third variable, right? And that is,
So what the left hand side equations that you've written, sir.
yeah.
So we can subtract two from one. So like since
Yes,
so
yeah,
we get
I understand that in this specific case, you can surely do that, right? But
yes,
you see,
yes.
ask yourself this question that if there are two equations like this, in two equations in three variables, I mean, are there always going to be infinitely many solutions? And the answer to that is no,
First of all, they have to be consistent. So we have that as one constraint.
right? And it is not clear why they're consistent in general, right? So
Uh,
why is it
yeah, in
consistent in
general.
this case that
So like you can see that
uh,
no one equation is like multiple of the other, or so like very rude in a very rudimentary way. Like you can say that.
right, right.
Like there's
Okay,
no lambda such that lambda times equation 1 gives you equation 2.
right, that is correct. Second. Yeah, so the question is only of consistency, basically, right? Apart from that, yeah, if you have consistency, then surely there is no problem, right? Yeah.
Right. Yes, sir.
So this is the claim that I'm making, right? If these two equations are consistent, then there will always be infinitely many solutions, right?
Yes.
That
Yes,
you
sir.
can see, yeah, you can try to see that intuitively at least to begin with, right? And so we
Yeah.
know that there are infinitely many solutions,
Right. Yes, sir.
right? So Virendra, is this fine? Is this so far, or do you have any alternative? There are much better ways to do this. Yeah. No, we cannot hear you. Your connection is, I think, not good. Yeah, so you should fix that. Yeah. Anyways, right. So, what would be no, I cannot hear you. I think it is like last day only. The connection is not correct. Yeah. Yeah. So you have to. Yeah. Anyways, so there is something to it which I am trying to get at. Right. So let me ask this question then. Like if I replaced this by just, as you can understand, arbitrary, then it becomes a very interesting question,
Yes. Yes, sir.
right? So find conditions on A so that there are infinitely many matrices B such that, yeah. So for which A does there exist infinitely many matrices B? So now it's no more this problem. So,
Yes. Think yeah. Using the same methods, it should be solvable. I mean, solvable.
oh,
So
but it
like,
won't, but see, but it is not true for any, it is not true for any A. It is
yeah.
not true
Like
for
we
every A.
need. Yeah. Yes, sir.
So for which A, like, can you put a, can you describe those matrices? So I'm asking question on describing all those matrices A for which there are infinitely many matrices B such that this happens. So how would you describe these matrices? Right? That is the question.
Uh. So like my idea is again to carry out the same multiplication and impose that we have consistent equations on like both
Yes.
sets of equations are consistent.
Yes, surely. Right. So let us see. So you want to say that these two equations are consistent. So we can write here so what will the coefficients be here?
A11 B11
Right. Let me
plus
write them with green. That B11 is fine. Those are the variables. Yeah,
yes
A21,
sir
A21,
A2 yes
right. I am trying to connect this with what we were doing last day about injective functions. So if a function f
okay
had a left inverse, then this is like a left inverse. A is like a left inverse. If you think A of A as a function, and if you think of multiplication of matrices as composition of functions, then B is like the G, such that the composition is the
yeah
identity function.
GOF
You're right. GOF is the identity function. And basically that's the question we are asking, right? And so, yeah, the question is when does function have a left inverse? And so we will answer that. You already know for sets, the answer is if and only if it is injective. Okay, but first let's just do this. You are almost there, so we will finish this and then. Move on. Virendra, please, if you have fixed your connection, then you should, yeah, tell us some, maybe if you know some linear algebra point of view also. Okay, so but we'll continue. Yes.
Hello, sir.
Now we
Now
can hear
can
you. Perfect. Yeah.
I change my earphones?
Yes. So my first question is that is everything so far, is there anything you want to ask here, first of all?
Okay, we changed A, generalized A. So
Right, we
that's
generalized A. So we had a, that's to summarize, always good. We had a particular A, and for that particular A, we concluded that there are infinitely many B's, so that BA is the identity matrix. Okay, and we if that is clear, right? We saw the argument there. Now we want to basically find out all those A's for which this happens. This is the nature of how we ask questions in mathematics, right? So yeah. Now let me continue. So A32. Yeah, so we have changed the A, we have made it general, and yeah. All right. Now, yeah, now Aryan, tell us if you know what should be the
Yes.
conditions for which for this equation to be consistent. What should be the sufficient condition?
So the condition is A11 by A12, A21 by A22, and A31 by A32. They can't all be equal.
Right, right. So you are just saying that, yeah. So you are just saying that C1 and C2, right? Uh, you are saying that C1 is not equal to lambda times C2,
Lambdas. Yeah. Yes. Yes.
right? So
Because
if,
like easily, if it were, then
yeah,
and
that,
lambda is non-zero. So
right.
yeah.
No, any lambda is fine actually, right? Lambda equal to 0 होने से भी if C1 is equal to, yeah, that's fine. That will also work, right? Yeah. So anyways, yeah. So first of all, if such a lambda exists, right? If C2 or if C1 is lambda times C2, then this equation is not consistent, surely,
Yes, sir.
right? So that I suppose we can see, right? So then basically this basically becomes this like this, and obviously it's not possible. This is not possible, right? Yeah. So if one so if C1 equal to lambda C2, then it is not possible. And if so, now I want you to explain, right, that if C1 is not equal to lambda C2, then why are these two equations consistent? Show that this is consistent. Yeah, let's see. If anyone of you can explain that. I think it's easy. I'm just asking a very easy question, I think.
So, but like it's. So now we have. Okay. Oh, 1 second. No, no, sir. 1 second. So if we consider the line segments in R3,
Okay.
or the lines actually made
Okay.
by these. Like since we have this C1 not equal to lambda C2, we get that they're not parallel.
Okay.
So or anti-parallel. So they must
Okay.
intersect at a point. So they have a unique solution. But of course we can vary B13 and like change the intersection point. But no matter what our choice of B13 is, since these two lines are not parallel, they have an intersection point. So like they have a solution.
Yeah. So you're talking about C1 and C2 as your lines.
Yes, yes, sir.
But C1 and C2, so lines, see, so are your lines passing through the origin?
Think so that depends on like the setup itself, right? Like
So, but if you have,
Second
yeah,
second line is passing through origin, sir. I mean, it can
uh,
pass
s-
through the origin.
second line,
If we consider A12 B11 plus A22 plus B12 plus A32 B13 as line,
uh-huh.
this is passing from origin.
No, but how is this, like, this thing is not a line, right?
Okay, if we consider
No, but it, right, but in what way? Like that is that's not a line.
so no, so we take A1 yeah, we take A11x plus A21y plus A31z is equal to 1. We do
That's
the same
not a
A12.
line. That is not a line. That's a plane.
Oh, yeah, my bad, my bad.
Right.
Oh,
So you
no,
are
no, sir.
basically talking about plane.
No, so actually, no. It's a line itself because suppose we take B13 to be a constant and not a variable, then we'll get a line. So for now, I'm just taking B13 to be a constant. Or like you said, we'll get a plane, and if these two planes intersect, then we'll have like a consistent system.
Right. So basically you want the two planes to intersect. Right. So you can think of it in
Yes,
terms of planes. Right. Right. So you think of these things as variables. Right. You think of those things as variables. Then you have a plane, and you have this plane, and you have this another plane. Right. And these are variables. Okay. And these equations decide a plane. Now your condition is basically saying that the planes are not parallel, right? This is basically saying that the planes are not parallel. That you have to figure out,
yes,
right?
yes, sir.
Because this A11, A21, A31, this vector is the normal to the plane, right? And the normals are not, you see, the normals are not the same thing, means that the planes are not parallel, right? That's obvious. So the planes are not parallel, so they will intersect. And if they intersect, it means they intersect
Right,
at
yes,
infinitely many points.
yes.
That
That's
infinitely
kind
many
of
gets,
what I was trying to say. Yes,
right, infinitely many gets taken care of, but yeah. Only thing is the consistency, as we were stressing on,
yes,
right?
yes, sir.
So then that is fine. And then the second one is same, right? So we really don't have to worry about it, right? That comes in the same way. Beautiful, right? So, I mean, so what we have kind of noticed is that if there is an inverse and there are infinitely many inverses, and we have completely said when there is an inverse, in a way. Okay. Now let us just sit back and compare this with function business. Okay. So with how we can interpret this in terms of functions, and you can see basically then you can actually give a much more elegant answer. Even if one was a m by n matrix, then also you can give an answer. Okay, quite a clean answer in terms of ranks you can give, but we will not go into that. But yeah, so first I want you to view this a which we have as a function from, so we will try to view this a as a function from between two spaces. So what should those two spaces be? R2 to R3, correct? Because this matrix, right? If you give it a vector in R2, it returns a vector in R3. No question, right? That is clear. So that's what this does, right? And it actually sends E1 to the C1 that we have. E1 means 1, 0, and it sends E2 to C2. Now things are interesting, right? Now you tell me, so this function is clear to you, right? And this function is completely governed by this matrix, right? If it sends E1 to C1 and E2 to C2, any vector now you have here 2, 5, where that will go, you know very well. Just multiply it with this matrix, or take linear combination with those columns. But all the details we don't need to know very properly. That is not completely needed. Okay? But I'll get to the point. That is, tell me, when is A injective? When is this function injective? Yeah. So you know when is A not injective, right? When is A not injective? So if E1 goes to C1 and E2 goes to some lambda times C1, right? These are all vectors, right? Then can this function be injective? No, right? Because if E2 goes to lambda times C2, it means that this goes to C1, which you can see now. It means that two different vectors are going to the same vector, and so it is not injective. Correct? Okay. So I will just write this and leave that. Whatever you said, whatever Aryan said earlier, that about it's the same thing. So A is injective, and this point of view can be very useful. Okay. So A is injective if and only if C1 is not equal to lambda times C2. You can see this. You can prove the reverse way also. Right? So if A is injective, then certainly C1 is not equal to lambda times C2. And if C1 is not equal to lambda times C2, then also you can show that A is injective. That you should again write that for homework. Okay. So this we have, right?
Yes, sir.
You can, if you can see that it's good, otherwise you should do that for homework. So now A is injective if and only if this happens. Okay. Now this we know that this is if and only if B exists. We did this just now. Okay. And now you see, now A is this function. So now this basically, yeah, so this is basically, now B exists is basically saying that the function A, now think of it as a function, right? A of B is identity, or A of B of X. Let me write it like that actually, because that's the notation we have been using, right? You know that this should be, yeah, it's a vector, but it's just not the point, right?
So it's sort of like the Schroeder-Bernstein theorem. A is
No, no,
injective implies it has an inverse.
no. It is no. So that's the point. This is not an inverse. This is a left inverse. This will not be a right inverse.
Okay. Oh, yeah.
Okay.
Forgot about that.
Yeah.
Yeah,
And
because AB is, yeah.
yeah, and you can show that there is no matrix B such that AB
Yes.
is equal to identity. That is another homework you can try. That's very simple actually. There is no matrix such that AB is equal to identity. Means the opposite. This is never possible. This is not possible. You can show, and it's easy to show. Yeah? So you can check that, but I will not go in that one. I want to compare this with something very nice. Okay. what do I want to compare this with? So now you look at just functions on sets. Okay, what do we know in sets? So if f is a function from a set, there's something very nice waiting here. That's why I'm telling you that you see this function which is from S1 to S2, right? We know that f is injective. And this again, if Virendra, if you don't know this, then you should check this. You should try to prove this, that f is injective. This at some point you would have seen. Then f of g of x, then I should not say like this. Then there exists a g from S2 to S1, but that I'll not write. That will be follow from this thing, so I will not write it. Such that this, I'm not trying to be super compact, but I'm just trying to be efficient, like trying to get the idea across. Right? We know this, right? If there is a G, then surely F is injective. And if F is injective, then there is a G. This we always know for sets. It is true. Now that G may be a very, very bad G, but it will be true, right? So if F is an injective function, one function, right? Then we know that there is always a G such that this becomes identity. Okay. Why? I mean, if you want to just see it in pictures, it is very, very simple. Suppose there are 3 points and they're going to 3 different points. Okay. And then there's a 4th point or 5th point also. You can define a G in the reverse direction, right? You can just say, okay, I will send these points where they should to reverse the function. And these other points, you can send them anywhere. It doesn't actually matter, right? It doesn't actually matter that. So for your G, because G is only bothered on its on fx, it should be identity. So it's easy. I mean, but if you prove it, you see that it's not completely easy when you prove it for infinite sets. But anyway, this we know. But what I was trying to say is that something is injective means that it has a left inverse if you allow G to be any, if you allow for G to be any function. Now we will discuss this thing about continuous functions, let's say, and you will see it is not true. Okay, injectivity and inverse thing. But for sets, it is true that if f is an injective function, then there is a G such that G times f is identity. Okay, it may be a bad G. But in linear algebra also it is true. What is special here? Special is that this B is not a bad G. That is why it is special, right? There is a B, we always know that A is injective function means there will be a B, but there is a good B. There is a matrix B, a function which is given by matrix, which produces the inverse. So that is the picture. Okay. Now you should try to, before the break, think of, means during the break, after 5 minutes we'll meet, but think of this. So try to take a function from R or some subset of R so that it is injective. F is injective, but there is no inverse of F. There is no continuous inverse. Okay. Injective and continuous and has no left inverse. We'll meet in 5 minutes. So please join after 5 minutes. Okay.
Oh, so in this F from R to R, F is
It's continuous and injective, but has no left inverse G, which is also continuous.
That is continuous.
Right.
Okay, okay.
Otherwise, it exists,
Right.
you know. Okay, so we'll meet in 5 minutes. Join in the same link.